But first, the next 4 relatively short presentations are going to focus on the transport research work that's been undertaken or which is planned using DAFNI. As Marion said, I'll be introducing the NISMOD transport model, then my colleague Marcus Young will show further examples of rail modelling using DAFNI, and my DAFNI champion colleagues, Just and Christian, will explain their research using the facility. So I'm going to give a very brief overview of the NISMOD modelling suite, which was developed as part of ITRC, the Infrastructure Transitions Research Consortium, before focusing on the transport model and some of the recent research using the model undertaken by the model developer, Milan Lovrich, Simon Blaney, myself and others. Then looking briefly at how some of that work is being used to test the new implementation of NISMOD on DAFNI, and how some of the outputs for the transport model will look using DAFNI's future visualizations. First, I want to say a little about ITRC and NISMOD, the NISMOD, the National Infrastructure Systems Model, which was developed initially as a series of interrelated sectoral models representing Britain's national infrastructure networks. Those models were most notably used in assessments for the National Infrastructure Commission, while other work in ITRC focused on assessing climate risk and vulnerability. And that results from that work have been used by DEFRA and the Environment Agency, among others. The second 5-year programme of ITRC is ITRC Mistral, which is framed around developing those sector models at different scales, which has given us the opportunity to consider outputs at a regional scale, which the consortium undertook for the Oxford-Cambridge Arc, which I'll come on to briefly. If you want any more information about ITRC's work, then the website shown here is the best place to start. This shows the complexity of NISMOD. This graphic was developed by one of my ITRC colleagues from Oxford, Tom Russell. To try and put this simply, we have a range of options for generating future demographic and economic scenarios, those green boxes at the top, along with 2 orange boxes which represent strategic or rule-based approaches to how the future infrastructure systems might change or be used. And together they generate the model inputs which go into the models at the bottom. I'm vaguely aware of most of these models, but it's the transport model that I'm going to focus on today. The transport model is based on the British road network. It's got underlying data which mirrors the Department for Transport's counts and estimated flows on the major routes. And there's an associated origin destination matrix, which is used to calculate and generate future route choices. The model is designed to assess the impact of a number of input variables, such as population change over time. This shows the population projection for a specific housing growth scenario in Hampshire, compared with ONS projections. There's some work we're currently undertaking for Hampshire and Solent Transport. Or perhaps we can consider the changes to the vehicle fleet in terms of fuel types or engine types, for example. So we can compare the differences between a slow version and a more rapid change towards electric vehicles. The model can also incorporate changes to the road network in terms of capacity enhancement or other interventions such as congestion charging zones. So for a given socio-demographic scenario, the model predicts a range of metrics, including travel times, energy use, vehicle kilometres and emissions. And these metrics are disaggregated in different ways, by time of day, for example, by road type and vehicle type. And the outputs are spatially disaggregated at the local authority district level. We also have models for railway station and airport demand, but today I'll be looking solely at the road model. So I want to give you a flavour of the model's capabilities. So let's look at a couple of projects which we've been involved in the last 2 or 3 years, which have featured outputs from the transport model. The Oxford-Cambridge Arc case study with ITRC, and a related project with England's economic heartland. For the ARC study, we wanted to demonstrate the capabilities of the whole of the NISMOD modelling suite. And we looked at the future impact of different population growth scenarios, which were based on the development of a significant number of new dwellings in the region, and the effect that that population growth has on infrastructure demand across multiple sectors: energy, transport, water, and digital communications. We looked at two main scenarios of development, and the graphic on the bottom left, which comes from work carried out by colleagues in Newcastle and Leeds, looking at the spatial options for new developments given particular attractors and constraints, shows those scenarios quite well. The top row shows expansion around existing built-up areas, while the bottom row shows how the development of new settlements within the region might be distributed. We also wanted to consider how to overcome some of the mobility constraints in the region, particularly the east-west connectivity between Oxford and Cambridge, which is relatively poor. So we also consider the impact of a new expressway connecting Oxford, Milton Keynes and Cambridge, along with some improvements to the regional railway infrastructure. An example of one of the options is shown here. Looking at some of the outputs from the transport model, this chart shows how emissions are likely to reduce over time, even though population's increasing, because we're assuming that there are more electric vehicles in the fleet and vehicle efficiencies are improving, all contributing to this reduction in emissions. We can see the impact of population change in these graphics, which show CO2 emissions in 2050 for each of these population scenarios. You can see its CO2 emissions are much reduced compared to 2015, but there are still pockets of higher CO2 emissions concentrated in the darker areas where the new housing has been introduced. We next used the transport model for a study for England's economic heartland, which covers a similar region to the ARC, with some additional local authorities making it slightly larger. For this study, we only had to consider one growth scenario, which is based on currently planned housing developments in the region extended to 2050. And you can see that there's much more variation in 2050 for those EEH growth scenario on the left compared with the ONS population projections on the right. So given this change in population, how do we meet the target of net zero carbon emissions by 2050? Well, there's a number of different approaches we could consider, and we've developed a small number of different pathways to reach this end goal. We've made one major assumption that, except for the business as usual pathway, all vehicles are zero emission vehicles by 2050. So essentially we achieve the target. When actually getting to that situation has its own particular set of challenges, and we'll need some major changes in legislation, in public attitudes and behaviour in the coming years. So while this is perhaps an overly optimistic set of pathways, this is what the EEH team wanted us to focus on. So as well as a baseline pathway, we've got three different approaches to decarbonisation. There's a highly connected future, which changes the way the transport network is used through embedded technologies. There's a future in which the vehicle fleet undergoes rapid technological change. And there's a shift in behaviour towards more sustainable transport. But the transport model has only got a limited set of levers that we can change to generate these pathways. So for instance, in the behaviour shift pathway, we introduce a road pricing measure in all the major built-up areas to discourage road travel, which acts as a proxy for behaviour change. For the adapted fleet pathway, we can change the rate at which electric and autonomous vehicles introduced to the fleet, so it's more rapid than the other pathways. And you can see how pulling these different levers can give us different results for each of the pathways. Let's look at some of the results then. Since we've assumed that all vehicles are electric by 2050, there are zero tailpipe emissions until 2050. But you can see that the more rapid technological advances in the adapted fleet pathway have a much more noticeable effect in the short term. But this impact in technologies is also evident for electricity use, which rises dramatically in all the pathways. But again, vehicle efficiencies for the adapted fleet pathway suggest that that may help to limit the demand on an energy system in the future. This graphic shows the average speeds in the road network by time of day. Those dips are showing the slower, more congested peak periods, and naturally higher populations will generate more traffic, so we can expect more congestion in 2050. But here you can see the effect that that road pricing measure has on the behaviour shift pathway. That yellow line is slightly less bad than the others, although it does look as if none of the pathways are particularly effective at tackling congestion. We've only got a few minutes here, and that's a bit of a whistle-stop tour of some of the capabilities and limitations of the transport model. For these studies, I've been running the transport model locally using Southampton University's high-performance computing facility. But since NISMOD is currently being transferred onto DAFNI, it should hopefully make it easier to set up new model runs, work with different data sets, and produce visualizations, which currently have to be done offline in Excel or Python. So I just wanted to share a couple of examples of how these visualizations might work once the model's up and running. These screenshots have come from Martin Robinson at Oxford University. He's working on developing the visualizations for NISMOD. And this output graphic actually is the same as the emissions data for the EEH study. I won't go into the details of what's happening here, but it shows the various options for generating a variety of visualizations from different types of data sources. Because most of the output data for NISMOD has a spatial element, we can use that to generate maps and other visualizations to help us tell the story about what the results actually mean, such as this showing different speeds on the road network at a particular time of day, which we can use to highlight congestion hotspots. Hopefully you can see that having this kind of functionality makes it a lot easier to generate new charts or other types of outputs from new model runs. While this is just one example from the transport model, I hope that with Bethan and Tom's demonstrations earlier, and with further examples from Marcus, Just and Christian coming up, we'll have given you a flavour of some of the potential applications for using DAFNI and how it might be applicable to your work. There'll be an opportunity to discuss that later, but I just want to hand now over to Marcus Young.